So Moore's law has governed our progress in compute for the past few decades. We've gone from room-sized mainframes to smartphones and GPUs that are dictating our AI future. However, we're hitting the theoretical limits of physics in a lot of ways we can make our computers, and we now need newer degrees of freedom in order to unlock these new computers that are still going to govern and decide our future. And so I have two gentlemen here. It's my pleasure to have Chris Anderson from Xlight and Mike Lafferty from Snowcap. Welcome to the family. On stage here to talk about a couple of those degrees. All right, so please introduce yourselves. Give us a little bit of an introduction of the companies you're working with and what you guys do.
I'll start.
Yeah, Chris can start. Sorry.
Hot here. Yeah. So hey everybody, I'm Chris Anderson. I'm a VP of Photon Systems at Xlight, where we're developing the world's most powerful lasers that will revolutionize semiconductor manufacturing. By making today's manufacturing technology do a lot more, but also enabling next generation manufacturing technology. So my background is I spent about 17 years in the national labs developing a technology called EUV lithography, which, as many of you know, is the key enabling technology used today to print the transistors on our silicon chips in the manufacturing process. And you talk about deep tech. So EUV lithography really was a 2+ decade kind of technology in the making. And the group I was part of at Berkeley Lab worked with tier 1 foundries and all the tier 1 semi-capital equipment manufacturers during the kind of development phase of EUV lithography to kind of, in many cases, pilot and prove out the kind of critical enabling technologies along the way. So I really got to kind of ride the whole arc of taking that from the R&D phase to the commercialization phase. And so now at Xlight, I kind of view this as this opportunity even at a grander scale. So our laser systems will now allow EUV lithography to really reach its fullest potential. At the same time, they're planting a seed for the next generation manufacturing technology. So really excited to be here, Rahul.
A quick fun fact about Chris, he famously tested 15,000 materials as he was thinking about getting to the 1 nanometer future. So we'll ask him about his favorite material later on. But yeah, Mike.
Thank you. Yeah, Mike Lafferty, Snowcap Compute. So we are building superconducting digital compute. So conventional digital technology that we all know and love in CMOS, converting that into a superconducting environment, running at 4 Kelvin, getting order of magnitude improvement in performance and 2 orders of magnitude improvement in power. So trying to keep a minimum step in this evolution to higher performance, lower power compute. My background is started as a process engineer about 30 years ago before jumping into digital design and ultimately coming to work at Cadence Design, so EDA software company. And the motivation to going to work there was to support 2 of my other founders, Anna and Quentin Herr, who came up with the physics and the working model behind these devices that we're using to build this technology. But they were lacking the EDA software and the environment required to build CMOS-compatible scale systems, to actually go to that next level and build systems that could compete or go beyond what CMOS can even envision today. So I spent the last decade of my career working at Cadence to build that EDA software ecosystem. So now we have a complete solution that we can realize these large-scale superconducting digital systems.
Awesome. Fun fact about Mike, the group he used to work for at Cadence was called More Than More. So this feels like a very appropriate panel for him to be on. So since we are talking about Moore's Law, question to both of you. Chris can start. Is Moore's Law dead?
So the one-word answer is no, but I'd add a footnote, which is I think, look, we have to be realistic that the trend is slowing. So Moore's Law states that the number of transistors per chip doubles every 1.5 years. I think many people are saying now it's more like every 3 to 4 years. I think also the definition of a sort of chip, I think, is loosely evolving as we're moving to advanced packaging and multiple chiplets kind of being assembled together to make what we're calling a chip. So those are my two caveats. But I would also, I think this is actually a good opportunity to add that as we're approaching these fundamental scaling limits, and we're not going to be able to put higher density of transistors on chips, I think we need to start thinking about kind of at a planetary scale, like how many chips can Earth, or how many transistors can Earth manufacture per year? And what's the derivative of that look like? Like how does that rate change as we kind of go past 2030, 2032 into the next couple decades? And so when you ask yourself that question, you kind of get to some interesting insights about what has to happen to the machines that actually print the chips and what we need to do as a planet to kind of continue this exponential curve.
That's super helpful. And so, Mike, what's your take on this? You've obviously taken a pretty orthogonal approach to try to do a step change in Moore's law. Is that Mike's law or Anna's law? But what's your take on if Moore's law is dead or not?
Yeah, I guess in the simplest sense, if you're going to argue it's a law, then it's dead, right? Slowing it down would violate the law. So in the simplest sense, yeah, I guess it's dead. But if we look at what the technology's been doing, it has been slowing down. We are still increasing those transistor counts. But are we? We're increasing the theoretical transistor counts, but what's actually being realized on silicon is not that. We can't deliver enough power, we can't remove enough heat. So although the technology is advancing to be able to deliver those transistors, we can't actually realize those transistors. So from that sense, Moore's law is definitely challenged, right? Now to your point, right, chiplets and other promising solutions, which were all also part of Moore's law, not commonly thought about as much, are showing promise. The industry continues to evolve and take advantage of some of those solutions, but there's challenges, right? The communication bandwidth from chip to chip is still a challenge. That adds more power and more heat in order to solve those problems, which are part of the fundamental issue you're trying to remove. So I still don't see it as being a savior. What I see it is instead, we've been stuck for the better part of a decade, kind of bouncing against this wall of trying to keep Moore's law alive. And the reason Moore's law exists, right, is that's just human nature. It's human need to want to double that performance in that kind of time scale. It's just humans do that with everything. So that desire is still there. So the challenge is it's moved beyond the chip and the transistor to the system level engineering and the solution around it, to the entire data center, for example. And we're pushing engineers in all different aspects in order to get to that solution. But I think we're really at a point where something needs to change. Because, and it is, right? Even in the CMOS world, it's changing. Backside power is coming, other solutions are coming, stacked CFETs and other devices to try to keep this alive. But the money will keep flowing to make it happen. Right? The people will demand it. They're going to want it. The solution's going to come somewhere. It won't be transistors doubling, but it'll be something else to make the solution still work in the system level environment. And I think we're still seeing that occur. So Moore's law to what it says is a law, yeah, I'd say it's dead. But the reality of what it intends and what it's trying to demonstrate, it's alive, but it's struggling.
So Chris, Mike says Moore's law is dead. You're trying to extend it. What technical breakthrough allows you to productize this new sort of world with X-Light's most powerful lasers? Like, why does the most powerful laser matter here?
Sure. So it's actually, I'd say, more than just a technical breakthrough on this specific question. So there's also like a market landscape aspect to why now for this technology. So EUV lithography has reached mass adoption, right? All the tier 1 fabs are using it. It's being used to make all of Anthropic's and NVIDIA's, training chips and all this stuff, right? Yet the EUV chip printing machines are just literally starving for more light. Okay, you go talk to anybody on a process line at a fab today, they all want more photons to make the machine do more and work better. Okay, so that's kind of the market landscape. And there's just no, with the current source technology roadmap, there's just no way for that to get to where it needs to be. So it's basically ripe for a technology solution. Now, meanwhile, in the background, superconducting RF accelerator technology, which is kind of the core tech X-Light's built on, this has been slowly maturing in the national labs since the 80s. Okay, and it's been progressing and progressing each decade, and right around the 2010 point, kind of got to the point where it was really at a system level mature, the supply chain was mature, the know-how to manufacture all the components was there, and so it's this kind of perfect sort of matchmaking moment with the market opportunity and this technology that was really waiting for its kind of moment to shine, commercially. So I think that's where it is.
And Mike, so in terms of a technology breakthrough, superconducting logic is not new, right? So what is the breakthrough you and the team have discovered recently, and why is now a really good time?
Recently, we've been working on this for decades, so it's been a long time in the works. There's a lot of things in the market that have come together to really make this happen, right? The quantum industry itself pushing cryo cooling has been huge. Right? Fundamentally, we've taken the problem that people are trying to solve in the CMOS world of building high-performance computers and then trying to get the heat out and cool them in that respect. And instead, we've stood the problem on its head. We've taken something very cold, and we've started communicating with information right at the thermal limit. And we said, what can we do at the thermal limit and still maintain that cold temperature the entire time? And by building the compute platform around that, we can solve where CMOS has been stuck. Now, interestingly, we found we can go back to 28 nanometer, a 15-year-old technology, and we can exceed what 3 nanometer CMOS can do for performance, power, and everything else. So we've stepped back in time on the lithography side for now. Obviously, we have desire to scale that, but it's good enough to step back to what would be considered a legacy node now and demonstrate what can be done there. So the advances are really around how we can generate the power distribution networks to hit the device densities that are required to be compelling as a competitor to CMOS.
And these two seem like really difficult system engineering problems. A lot of components and subcomponents and systems have to come together to make this work. What are the challenges of building such hard technology? And what is the time frame which we'll see such technology out in the wild?
Sure. So from my perspective, I think the manufacturing is ultimately the hardest challenge, especially for an X-Light scale system based on a particle accelerator. And I think that the way to solve that, our approach, is modularization. You want to minimize the unique number of parts in your system. You want to get good at manufacturing the things that you do need to make, and stack those things together. I'm often reminded of the story of the Empire State Building, which we all know about that in Manhattan. And at the time, it was this incredibly ambitious project, but it actually came in under budget, ahead of schedule. And the reason that happened is that the people erecting that building, the people making the beams and all the supply chain, they didn't feel like they were building a complex 100-story tower. They felt like they were building a simple one-story building and replicating it 100 times. And I think that's been tried and true many, many times in industry. And so, yeah, we do a lot at X-Light with our design to have it be highly modularized and have replicated components throughout the system. So yeah, manufacturing.
Awesome. And Mike?
It kind of makes my job sound a little bit easier. A lot of the pieces for us are actually built. The cryocoolers exist. 28 nanometer fabs exist. Spent the last decade building up the EDA software, so that environment exists. So really, we're just bringing all these pieces together now. So we're not inventing new manufacturing methods or processes or anything else. We're simply executing on existing infrastructure that's out there. we've spent decades getting that in place as a team, so the work's been done in the past. But in that respect, it's not a huge hurdle. So obviously we have to put it all together and demonstrate it to the world and show it can be done. And the timelines with that are relatively near term. We're talking single-digit years, not decades or anything. But yeah, let's just put it together, execute, show the world what can be done, and just grow from there.
Yeah, that single-digit years is music to all the playgrounders here. So.
Yeah, I didn't actually get to comment on that, but yeah, similar timeline for an X-Lite system. Yeah, and I would also like to add too. You mentioned that a lot of the stuff you can sort of buy, quote, off the shelf in air quotes, right? And yet one of the other kind of key things for X-Lite is, although it's not necessarily off the shelf, all of the manufacturing technology already exists. So we're not having to actually go out and invent that, which is key.
And the key to that is obviously a lot of the work that's been done in the national labs in this country. And bringing all of that together in the commercial sense is obviously new. But the research exists, and you're working with the said national labs to bring it to light. In terms of inflection points for the company, right? This is a long journey, and hopefully it's single-digit years and on the lower side. You'd need a bunch of capital, and you need to show a bunch of inflection points along the way to show progress. What are these inflection points like, technically, commercially, on the talent side? What do these look like while you're building this company? Mike can go first.
Yeah, so the inflection points for us, the critical thing, of course, is getting those first test chips out and just demonstrating to the world what they can do. From that, you can easily measure the power performance and predict the scaling that you can achieve for any design beyond that, because we're fundamentally built on a CMOS platform. We're using a totally different type of physics and a different way of getting the job done, but because we're built on what's known in the CMOS world and can be simulated and emulated in the CMOS world, we can directly scale the CMOS numbers to our environment. So the beautiful inflection point is get those first test chips out, build a workload that no one can argue with the output and the performance of what we're doing, that we can directly represent in the CMOS world as well. Once the world sees that, opening up the technology to others to show what they can build in it is really what we need to do to enable. So very quick inflection point, very early in our product cycle. So we're excited to go out and show that here in the near term and see where we can go from there.
So the first chip comes out. What is the one figure of merit you're most excited about showing to the world?
What we're going to demonstrate is performance per watt. So, we think that's the most critical thing to demonstrate initially. Obviously, there's just raw performance as well, which we will demonstrate with that system on day one, because we will be building a 30 gigahertz digital design. So raw performance will be demonstrated, but the most interesting figure of merit that we're looking for is performance per watt.
And that'll be orders of magnitude better than anything else out there.
It will be. We'll start low. We'll aim for at least an order of magnitude better, but we can go much further than that.
Yeah, excited for that. And so, Chris, what about you? What are the inflection points, and what is the one figure of merit?
Sure. So I would say for us, a big inflection point is in establishing these strong relationships with the kind of tier one semiconductor companies, right? So semiconductor manufacturing is just inherently risk averse. And so, it's working through kind of educating folks on what is the benefit that our technology brings, and it's very clear, but everybody sort of potentially sees that in their own lens. And so it's taking the time to kind of really understand the business model of our light source in a modern fab. And yeah, I can share that we've actually developed some incredibly strong relationships with the important people in this industry that we need to. So one is relationships within the market, and then two, I would say, this is kind of going back to the technology stuff, is the coordination and relationships within the national labs in the US. So because a lot of this technology was pioneered and developed within the labs, as we're growing as a company, having relationships with them has been incredibly important. And so we do have these, they're called CRADAs, Cooperative Research and Development Agreements, in place with several national labs. We're working together to kind of harness this technology and this know-how to build these systems. And then the third is really, this is not as typical, I think, for startups, but non-dilutive funding, specifically from US government and state sponsors. There's obviously a massive interest to reshore semiconductor manufacturing that has spanned administrations even. And we think this is really important work, but we do view that funding as a critical inflection point. So on the first metric, I think, I imagine each fab would sort of have a different one, but I think the simplest one is just how many more wafers per hour can you print with your existing machine after you hook up our light source? And that's going to be huge. And then the second is more nuanced and subtle, but it's what new technology nodes can you access with the same machine you already have in your fab at the same cost that's enabled by our new light source. So I think those are two of kind of the low-hanging fruit metrics.
So what you're telling us is it's basically a cash printing machine, where you give it more light and you get more money at the end of it.
That's a good way of putting it, yeah.
Okay, awesome. So should this technology be built? What does the data center of the future look like? And what is the impact of this future? Chris can go first.
Yeah, so the kind of future vision is one of the things that's sort of always excited me about semiconductor manufacturing. And so when I think about, I'll kind of tell you about what the data center of the future looks like in my eyes and then work back to how X-Light helps us get there. So if you go into a data center today, all the actual chips are limited in form factor to a 1-inch by 1-inch chip. And that's actually, it's like not that big, right? Our wafers are 300 millimeters. And that's just a fundamental limit of the manufacturing technology. So I do see a world where you can just have chips of whatever size you want. Secondly, I see this world where an individual chip can contain IP from potentially limitless vendors. So you can have multiple different companies kind of specializing in their own specific hardware stack that can all be natively and monolithically integrated together on the same process within a same chip. That's just kind of unheard of today. The only way you can do that today is by each different vendor sort of manufacturing their own physical chip and then connecting them together in a packaging step afterwards. And then, so that's 2. Then 3, I would say, I'd like to see this world where low volume, medium volume, and high volume runs basically have cost parity. So right now, if you want to start a company that builds a highly specialized data center for some specific type of AI and you have this hardware, software, proprietary stack, like there's a tremendous amount of upfront cost for you to run a low volume number of chips due to the manufacturing process today. So I think now working backwards to how that vision's realized. And by the way, I think that it's totally great if the future data centers have a cryo plant and everything's cold and we're running off Josephson junctions instead of CMOS. You're going to need the technology to manufacture stuff very small regardless. But I think this unlock happens with a transition from analog printing to digital printing. Okay, so the analogy in your head is like a printing press versus a modern digital inkjet printer. So in one case, you have to lay out the plate with all the information and you're sort of stamping it to the page. The other version, you just have a digital stream of information that's like dot, no dot, no dot, and your paper's whizzing by and you get the thing out the other side. Now, digital chip printing can be unlocked with the right laser system powering the chip printer machine, okay? So a modern chip has roughly 10 terabits of information in it. So you need a very high rep rate laser and a highly parallelized write process, but photons actually lend themselves incredibly well to high parallelization because they don't interfere with each other as long as they're at different times. Yeah, so that's That's a big unlock that I think X-Light enables. And so, you know, I see that this exciting future kind of being unlocked. So it's like X-Light right now is basically providing this much needed boost to the productivity of the existing EUV fleet, letting that fleet reach its full potential, but also providing this potential revolution change to digital manufacturing.
Mike?
Yeah, data center of the future. We're working inside of this cryo environment. So obviously I see a very big cryo plant. But what happens inside of our data center now is much more compact, because we are superconducting on our chips, we're superconducting on our interposers. If you're operating inside of a superconducting environment, basically communicating with electrons is like communicating with photons. Dispersionless communication, very high bandwidth, no need for serialization or deserialization at your chip boundaries. So you can take any architecture and you could slice it arbitrarily small and not be overly penalized for breaking those into chiplets. So even if big chips I'd love, I can make small chips work with a small penalty. So it does work with existing methods and techniques. I still want to have an interposer that's wafer size or panel size that I could direct right to in order to be able to put a lot of chips on that thing. So I see a lot of benefit in getting to that kind of world. The data center itself, though, you can imagine a very different structure, right? The size of a data center today is set by the ability to get power into it and the ability to get heat out of it. You know, the latest NVIDIA systems are talking about 600 kilowatts per rack. That is insane, but the limit of how much power you can deliver and heat you can remove from that one small footprint, right? And that's what they're fighting for, to try to get that done. The argument is if we go the other way, start cold and build up, now I can take 100 of those racks and I can put those inside of one cryostat and the thing will burn a tiny portion of the power inside of that cryostat, because our switching energy on our junctions is 5 orders of magnitude lower than it is for CMOS. So I can run that same CMOS workload at 5 orders of magnitude lower power. So I can compress all those chips together into a very small form factor. I have to burn 3 orders of magnitude of that savings to run that cryo plant. Still gives me 2 orders of magnitude savings overall. So I can really shrink that data center physically to really pack those chips close together. And the beauty of that is the time it takes for data to travel back and forth across a data center is minimized, because speed of light matters on those large scale systems just as it matters on my high performance system. So if I can get those chips, you know, centimeters off of each other, I can really increase the performance of the overall system and get rid of all the power it takes in that data center to move that data back and forth across that data center. Because now I'm doing it at the noise limit, at the thermal noise limit. I'm moving those signals across this very small system. So envision taking, you know, 100 racks of compute, burning 300 to 600 kilowatts apiece, and shrinking that down to something that fits in a suitcase. It has a cryo plant sitting next to it that's huge, but it's all there to cool that one little tiny area now, which is doing what a large-scale data center was doing in the past. So overall, the cryo plant's still smaller than what those 100 racks would take up, so it is a shrink of the overall data center. It's a massive reduction in power at the wall plug, orders of magnitude reduction in that wall plug power. But the amount of compute and the latency improvements are just insane, right, of what we can really achieve.
Yeah, I still remember the first one-line pitch of Snowcap was data center in a shoebox, so looking forward to that happening. And so I think we have a minute or so left. I thought it'd be fun to ask both of you, since you're pushing the limits of material science to the, you know, to its edge. What is your favorite material? Chris, out of the 15,000, maybe one of them, and, you know, Mike after that.
Sure. Well, I guess I have to leave a slight background, but in 2013, there'd been a lot of work on EUV lithography. It hadn't reached production yet. The morale was like low. Like if you went to the EUV conferences, like people were seriously doubting it. And right at that time, this completely novel, when he's saying material, you know, he's talking about the light-sensitive material that like captures the high-resolution image that you're burning into the chip. This totally new material platform came on the scene, and for like the whole time we had our chip printing machine in Berkeley, we didn't even know if it could print the smallest feature that physics said it could, because no material could even resolve it. And this new material came on the scene. It had like a crazy developer process that was like kind of dangerous, but we're like, what the hell? We'll give this a try. Let's take the safety classes. And it ended up just blowing the performance just off the charts. And so this was like, in my mind, this sort of wind in the sails of EUV lithography. I still remember it when we presented it at the conference. It was like practically a standing ovation about, oh my God, like there's actually hope for materials that can actually resolve to these feature sizes we want. So that material was developed by a company called Impria. And it's now called a metal oxide resist, the technical name. But yeah, so that was a long answer, but.
Metal oxide resist it is.
Yes.
Okay, what about Mike?
Yeah, we're a little boring in this aspect. The magic of what we were trying to do is we're trying to fit into existing CMOS fabs. So the trick is to find the right materials that give us the superconducting properties we need, but will not contaminate a CMOS foundry, so they'd be willing to actually manufacture it for us at scale. You know, we're not looking to build a fab, at least not on day one. So to do that, we need to be CMOS compatible to get to any level of production that's meaningful. Where a lot of the failures in the past 4 decades in this technology is simply people building in university labs, right? It's great. They have a clean room. They can do something, but they can't do anything of scale, and they can't truly prove what the technology can do at scale. So for our limitation, we ended up going back to niobium tinitride, which is well known for decades as a superconducting metal that does exactly what we need. But it was discounted years ago because of those legacy lithography techniques. Simply couldn't manufacture it to the quality control levels that are required. Those problems were solved as we got to 28 nanometer and below. So they're not a concern anymore. So we can utilize these materials that are well known from history that couldn't be manufactured reliably at these dimensions. Now they can, so we're simply bringing that together.
All right, Chris, Mike, thank you so much for joining us and talking about the degrees of freedom that you're unlocking. Thank you.